you will learn about the concepts of memoization and dynamic programming. Dynamic programming is a programming paradigm that promotes solving problems by breaking them into smaller problems and solving these. The solutions are then stored in an appropriate data structure for later use. The advantage to this is that if these subproblems require being computed again, one only searches for the answer instead of computing the problem again. The technique of solving subproblems and storing them to save time on a potential future lookup is known as memoization. Dynamic programming relates to two concepts already encountered in the previous videos. Let's have a quick refresher on these concepts. The first is divide and conquer. That is, taking one large problem and breaking it into a smaller set of subproblems and then solving these. The second is a subset of this, known as recursion. Recursion is the practice of coding a solution that avoids running loops, but instead uses multiple self-calls in coming upon a solution. Dynamic programming is an extension of these approaches, which in addition involves keeping a record of results generated from running the subproblems each time they are newly run. In subsequent runs, instead of recomputing results, a lookup is queried for the last time the question was asked. As said, this approach is called memoization. And to reinforce the concept, this is when the results of previous calculations are stored and used in place of rerunning the calculations when the compiler identifies that the computation has been run for a previous task. To exemplify this, consider the question posed in the video about binary numbers. How many combinations were possible with a binary lock of 6 digits? In a previous video, it was shown that you can discover this through exponentiation or finding the power of a number. So the same lock with 6 digits would have 2 to the power of 6 or 64 combinations. So 2 to the power of 6 equals 2 times 2 times 2 times 2 times 2. Alternatively, you can divide these into two groups where you have calculated 2 times 2 times 2 and again 2 times 2 times 2. That will result in 8 times 8 and again give the same result. Applying a divide and conquer approach to computing this efficiently using memoization would reduce the computations by first calculating to the power of 3 and again 2 to the power of 3. By applying memoization, the first 2 to the power of 3 would be computed, then reused for the second bracket, reducing the overall computation required. So, what sorts of problems are good fits for a dynamic solution? The dynamic programming approach is commonly applied to combination or optimization problems. One example of a combination problem already mentioned is the Fibonacci sequence. Another instance you may encounter in an interview is the knapsack problem. This is both a combination and an optimization problem. Say for a planned camping trip, you can fill a knapsack with required items. Each item has a weight cost to it. A torch equals 1 kilogram, water equals 2 kilograms, and the tent equals 3 kilograms. Additionally, each item has a value. The torch equals 1, water equals 2, and the tent equals 3. In short, the knapsack problem outlines a list of items that weigh different amounts and have different values. You can only carry so many items in your knapsack. The problem requires calculating the optimum combination of items you can carry if your backpack can carry a certain weight. The goal is to find the best return for the weight capacity of the knapsack. To compute a solution for this problem, you must select all items that add up to a given weight and contain a given value. The weight carryable will change. This problem can be applied to resource allocation, where you have so much CPU power and X tasks to run, just like the capacity of a CPU dedicated to completing tasks. Sometimes the weight will be 7 kg, and other times it might be 10 kg. Dynamic programming involves saving the computations used to come upon a given solution. So, If you have computed an optimum selection for 7 kg and it is raised to 10 kg, you will not have to rerun the initial computations again. This can be a time-saving metric. When computing dynamic programming solutions, you must firstly determine the objective function, that is, the description of what the optimum outcome is to be. Next, you must break the problem into smaller steps. One approach already discussed for achieving this can be the use of recursive functions, that is, functions that will call themselves repeatedly until a solution is come upon. They should be written in such a way that you can change the outcome without altering the code for the methods already written. To conclude, in this video, it has been shown that dynamic programming is an approach that looks to optimize solutions to a given problem. It uses principles of memoization and overlapping subproblems to identify when an objective function can be achieved quickly, optimizing the computation steps required. In this video, you will learn how you can implement this paradigm to solve complex problems by using greedy algorithms. There is a philosophical principle called Occam's razor. It states that the simplest solution is almost always the best one. This problem-solving principle argues that simplicity is better than complexity. In our case, the greedy algorithm is the simple solution. This is an alternative approach to dynamic programming, as this approach seeks to present an immediate solution for a task and favors local optimization over a more holistic global approach. When engaging with a problem subdivided into segments, utilizing a dynamic programming approach would find a globally optimal solution so that each subproblem is solved and the best subset is selected and implemented. A greedy approach would instead look at the list of solutions and implement a local optimization. Usually, the current most rewarding option is chosen. To make this more clear, let's take an instance of a CPU that has a list of tasks to be completed. Applying the dynamic programming approach would entail selecting a subset of activities that could be completed within a given time and executing these tasks. With the knapsack analogy, this would involve determining what subset of items to pack that would maximize the value in the process of filling the bag. A greedy algorithm approach to this would be always to select the most valuable item and place this in the bag, giving no thought to what other items this would exclude from the process. Thus, in our CPU example, a greedy approach would involve selecting first the shortest running program and then the next shortest program, and so on. While this might not lead to a globally optimized solution, it will reduce any overhead in calculating the most efficient subset of items. To better understand how these two approaches would differ, let us consider the problem of the shortest path. The image shows a map with 9 different nodes: A, B, C, D, E, F, G, H, and S. Each node is connected to another node by a weighted path. This weight reflects the cost that would be incurred by selecting this path. Thus, in our CPU example, a greedy approach would involve selecting first the shortest running program and then the next shortest program, and so on. While this might not lead to a globally optimized solution, it will reduce any overhead in calculating the most efficient subset of items. You are now faced with making a journey from E to F and want to plot the most effective route. A dynamic programming approach would involve creating a table and calculating each potential node from E. From there, It would introduce the next set of nodes and calculate the accumulated cost. This approach would undoubtedly arrive at the most efficient solution. Using memoization, after the initial calculations were made, they would be saved, and subsequent journeys would benefit from a quicker computed time. This is a bottom-up global approach to the problem. A greedy approach would differ in its methodology. Instead of trying to find an optimal subset of connected routes, it would instead begin at node E and look at each available connection. Thus, it would have a selection of weights, namely 5, 3, 2, 4, and 12, which correspond to nodes C, B, D, G, and H. The lowest value in that array is 2, which corresponds to node D. Following the greedy principle, it would make this selection and progress to the next node. Assuming that the data structure was a directed graph, it would be presented with a further 3 nodes, A, F, and G, that have the values of 7, 5, and 6 respectively. Since F is the final location, it would select F and arrive at its destination happily, having amassed a total penalty of 7 for travel time from E to D and then to F. That carries a weight of 2 plus 5. Visually, you can see that this is the most efficient approach, and it was come upon without creating an exhaustive table of combinations and computing all routes. However, had the node between G and F had a penalty of 2, then it would have selected a less optimal solution. This is the trade-off when choosing a greedy approach over a dynamic one. While the overhead for a greedy algorithm is low and coding a solution is quite straightforward, it will not always guarantee that the best option is returned. You now have a greater understanding of the greedy algorithm approach. In addition, you have seen how it compares with a dynamic solution and thus deepened your grasp of the strengths and weaknesses of this alternative approach. Next time you are plotting a route in Google Maps, consider the selection of routes that are offered and think about how these routes might have been calculated. In this video, you will learn Well done! You've reached the end of the Working with Algorithms module. Let's take a few moments to review what you learned during this module. You began the module with a lesson on sorting and searching. First, you learned about why sorting is important and explored the three main methods for sorting: selection, insertion, and quicksort, and examined the steps involved for each method that these algorithms use to sort data, and explored the strengths and weaknesses of the three sorting approaches when choosing an algorithm to use for a given solution. Importantly, that there is not one sorting algorithm that provides the best results in every given scenario. Next, you learned about searching algorithms, which are a fundamental concept in computer science, and some of the various methods that are used by algorithms for searching. You explored two core approaches to searching: linear and binary. Linear searches progress through every item in a given data structure until a specific item is found, whereas binary searches half the search space at each iteration. You also learned the steps involved in implementing both approaches and some of the advantages they offer. You also took a deep dive into time and space complexity for both searching and sorting algorithms. You then moved on to the next lesson, where you were introduced to working with algorithms. Here you learned about different approaches to working with algorithms. First, you explored the divide and conquer paradigm. In the divide step, the input is split into smaller segments and processed individually. In the conquer step, every task associated with a given segment is solved. And the optional last step, combine, is combining all the solved segments. And you discovered how the divide and conquer technique offers an effective framework for problem solving and the various benefits that it provides. Next, you explored another important algorithmic approach, recursion. Recursion is when a function calls itself with a smaller instance of a problem repeatedly until some exit condition is met. And you learned that there are three requirements for implementing a recursive solution, namely the base case, the diminishing structure, and the recursive call. You were then introduced to dynamic programming, which is a programming paradigm that promotes solving problems by breaking them into smaller problems. You explored the concept of memoization, the technique of solving subproblems and storing them to save time on a potential future search. And you examined the process involved to compute a dynamic programming solution. Essentially, this can be outlined as first, determining the objective function. That is the description of what the optimum outcome is to be. Next, breaking the problem into smaller steps, and then deciding which dynamic programming approach you would like to apply to achieve your desired outcome. Finally, you learned about greedy algorithms. In comparison to the dynamic programming approach, a greedy approach would look at the list of solutions and implement a local optimization. Usually, the current most rewarding option is chosen. You explored how a greedy algorithm approach could be implemented to reach a solution, and that there is a trade-off when choosing a greedy approach over a dynamic one. While the overhead for a greedy algorithm is low and coding a solution is quite straightforward, it will not always guarantee that the best option is returned. With all the knowledge you have acquired, all that is left is to complete the final quiz for this module before moving on to the final module, where you will complete the graded assessment. And then you've really made it. You're so close. Good luck and enjoy the rest of your journey. In this course, you have learned a range of concepts and skills as you prepare for a coding interview. Let's take a few moments to recap the key topics that you learned about. In the first module, you started by discovering what a coding interview is, what it can consist of, and the types of coding interview that you might encounter. Your first lesson focused on the technical coding interview, primarily to determine that you are technically capable of the role's responsibilities. You learned about the steps that you must keep in mind when this interview is conducted. You were taught that using the appropriate tools is always important and that you have to keep time constraints in mind. You also explored how you can prepare yourself for a coding interview and the importance of first impressions, including a focus on communication, such as explaining your thought processes and handling mistakes. You learned about the STAR method and how to use it to your benefit when communicating with interviewers. You also learned about how to work with pseudocode to demonstrate how you might reach a solution, some important tips for practical solution design, and how to test your solutions. In the next lesson, you got an introduction to computer science, starting with an overview of binary, where you learned about the difference between base 10 and base 2. You then discovered positional notation, the use of the position of the number to denote a progressive increase in value. You then moved on to explore key components of computer memory and how it works. You should know by now that to better understand the various layers of memory and should be able to describe the differences. You learned about the transfer rate, or the speed at which a computer can transfer memory into the cache for processing. You then moved on to time complexity, where you learned how to evaluate time efficiency or gauge performance by the time taken to complete a task. You discovered Big O notation, which is a metric for determining an algorithm's efficiency. You explored space complexity, which is essentially the space required to compute a result, and that any decisions around space complexity are not just based on the speed of an algorithm, but also on how much memory capacity a given solution will use. There will always be a choice to prioritize speed or compactness. In the second module, you learned about data structures. This ranged from basic data structures like strings, booleans, or arrays to more advanced data structures like collections, graphs, and heaps, and how each one comes with certain benefits and limitations. You explored all the types of data structures and how they are classified into two main branches, linear and nonlinear. Next, you were introduced to stacks and queues, abstract data structures that both have specific characteristics around how elements are added and removed. When you visited queues, you learned that a queue is very similar to a stack in that it tends to have the same methods. It can create, insert, remove, and check the state of the queue. Unlike a stack, a queue works on a first in, first out, or FIFO basis. Finally, you found out that trees are a powerful data structure that give you great flexibility in adding and searching values. Following this, you went on to examine some advanced data structures, namely hash tables, heaps, and graphs. Next, you explored heaps. You discovered how heaps can be used to organize elements from least to most important, and how, by limiting the functionality of heaps, productivity can be increased. Finally, you examined graphs. This structure illustration is a graph that is made up of nodes to denote destinations and edges that show how each node relates to another. The presence of values between the nodes mean that this is a weighted graph. There are no arrows present, which means that it is an undirected graph. In contrast to a directed graph, an undirected graph has no order of precedence. And you learned that a connection in a directed graph is considered weakly connected if the edge is only one way. However, if there are two connections going either way between two nodes, then it is said to be strongly connected. In the third module, you had an introduction to algorithms, including the types of algorithms available to you and how best to work with them to sort and search your data. You started by exploring sorting algorithms and how working with sorted data or having the ability to sort your own data can result in significant time savings. You discovered why sorting is important and explored the three main methods for sorting: selection, insertion, and quicksort. Next, you went on to discover searching algorithms and how each type provides its own framework for problem solving. You explored two core approaches to searching: linear and binary. Linear searches progress through every item in a given data structure until a specific item is found, whereas binary searches halve the search space at each iteration. You also gained insight into time and space complexity in both searching and sorting algorithms. You then moved on to the final lesson, where you were introduced to working with algorithms. Here you learned about different approaches to working with algorithms. First, you explored the divide and conquer paradigm. You learned that in the divide step, the input is split into smaller segments and processed individually. In the conquer step, every task associated with a given segment is solved. And the optional last step, combine, is combining all the solved segments. Next, you explored another important algorithmic approach: recursion. Recursion is when a function calls itself with a smaller instance of a problem repeatedly until some exit condition is met. And you learned that there are three requirements for implementing a recursive solution, namely the base case, the diminishing structure, and the recursive call. You were then introduced to dynamic programming, which is a programming paradigm that promotes solving problems by breaking them into smaller problems. And you examined the process involved to compute a dynamic programming solution. Essentially, this can be outlined as first, determining the objective function. That is the description of what the optimum outcome is to be. Next, breaking the problem into smaller steps, and then deciding which approach you would like to apply to achieve your desired outcome. Finally, you learned about greedy algorithms. In comparison to the dynamic programming approach, a greedy approach would look at the list of solutions and implement a local optimization. Usually, the current most rewarding option is chosen, and you looked at an example of how a greedy algorithm approach could be implemented to reach a solution. While the overhead for a greedy algorithm is low and coding a solution is quite straightforward, it will not always guarantee that the best option is returned. So, there is a trade-off when choosing a greedy approach over a dynamic one. Well done! You have covered so many important concepts and approaches throughout this course. It is a real achievement, but it should also serve to prepare you for any potential coding interviews that you may go on to attend. All you have left to do is to take the final course quiz before wrapping up the course. Good luck! You've reached the end of this coding interview preparation course. You've worked hard to get here and accumulated a lot of knowledge along the way. You've made great progress on your developer journey. You should now understand the unique and challenging aspects of the coding interview. Specifically, you should be well prepared with some interview soft skills that will help you to be ready when you go for your coding interview, the foundations of computer science, and some problem-solving methods to apply to any challenge you may face in an interview scenario. Following your completion of this course in coding interview prep, you should now be able to prepare for the interview process, offer strategy and tips for successful interviewing, and openly discuss the emotional components of the process. The key skills measured in the graded assessment revealed your knowledge and understanding of data structures in the context of coding interviews, the concepts and usage of algorithms, how to visualize an algorithm, and combining new and previously learned coding patterns to solve problems. Congratulations! You've successfully completed all of the courses in this program. At this stage, you may want to consider registering for another course, specialization, or certificate pathway. Certifications provide globally recognized and industry-endorsed evidence of mastering technical skills. Whether you're just starting out as a technical professional, a student, or a business user, the courses you have completed and the range of practical projects you have in your portfolio will prove your knowledge and ability as a developer. These can serve to demonstrate your skills to potential employers, and not only does it show employers that you are self-driven and innovative, but it also speaks volumes about you as an individual, as well as your newly obtained knowledge. You've done a great job so far, and you should be proud of your progress. The experience you gained so far will show potential employers that you are motivated, capable, and not afraid to learn new things. Again, congratulations on finishing this course, and good luck with the rest of your educational journey.